Okay, I think we are up and running. We can start talking about convolution. So why are we talking about convolution? It's a difficult math problem. That's why we need to talk about it. No, it's not the reason to talk about convolution. The reason to talk about convolution is because we want to compute the output of systems without actually having to measure them, right? If you tell me about the system and if you tell me what the input is, I will tell you, compute it analytically, I can tell you what the output is going to be like. I don't need to run through this input, find the output, measure it. I can tell you beforehand. I can predict the output. So you can do a lot of interesting things because of that functionality. How are you characterizing linear time invariant systems? Using the name of the system, using an identifier for the system, using something that characterizes a linear time invariant system. What is that? Impulse response, h of t or h of n. Once you know that impulse response, then you can do mathematical characterization, meaning finding the output. So how do you find impulse response? Well, give it the impulse, whatever comes out is going to be the impulse response. So for example, if you have a discrete LTI system, you give it a unit impulse, whatever comes out is going to be your impulse response, h of n. And if this was continuous, then you would be giving it an input of delta of t, you would be getting h of t. Now, once you have this, right, this is step number one. I have characterized the system. I asked the system what its name is. It responded with h of n. It identified itself as h of n. And once I know that, then I can find out any output for any arbitrary input. So once you know h of n, you will be able to compute mathematically the output of that same LTI system for any given x of n, any given input. And the way we compute y of n is running through this convolution sum. And we had derived this convolution sum in the last class. Essentially using the properties of linearity and time invariance, we were able to prove this. And the fact that we can apply superposition to these kind of systems. Next, how do you express discrete convolution in a mathematical form? You say x asterisk h. Right? The asterisk operator is going to be your convolution operator. Now, you will see me do this a lot of times today. Flip and move. All of that is to carry out that discrete convolution. Or if it was continuous signals, it would be for continuous convolution. There are three methods to deal with discrete convolution. Some of them are going to be pretty simple. Some of them are going to be a little bit tedious to work through. But generally, as long as you are in the discrete world, things are going to be relatively simple. Why? Because these are samples. These are values that you are doing these multiplication and summation on. So things are going to be pretty reasonable. When you get into continuous signals, that's when the things get a little bit more complicated. But we are going to try our best to sort of simplify the whole thing. All right, three methods. One, analytical, which essentially means let us compute this summation by evaluating the summation itself. And that will work really well if the signals that you are when easy for signals expressed in terms of step sequence. You know what happens when you express signals in step sequences? You are essentially bounding them, right? And when you bound them, you essentially evaluate the summation limits when you do that. Once your summation limits, instead of being negative infinity to infinity, they became bounded, it is pretty reasonable for you to carry out that summation. There is an array algorithm, which is a very systematic approach to finding the discrete convolution. It is going to be easy for small arrays, which essentially means if the values of x and h, the signals that you are trying to convolve, are limited, 3 elements, 10 elements, you can get done pretty easily using the array algorithm, which is essentially going to be distribute these elements, one on rows, one on columns, carry out the multiplications, and then add them diagonally. Pretty straightforward. Array algorithm, in order for computing convolution, is probably the easiest way to do it. There's no, the chances of you getting the wrong result are very small here with array algorithm, just because it's very structured, systematic approach. Then the last one is graphically. That's where you see me do this. Flip and then move it across. So when you're doing things graphically, you are actually, at each step, you are sort of imagining how the signals are moving, right? Graphically expressing the things. So we'll try to look at all these 3 variations. Graphically would apply for almost all situations. Let's take this particular system here. And we are exploring the first way of finding the response of LTI system. We are trying to do this analytically. What do we have for H? The impulse response of this guy is 1/4 to the n, u of n, right? Step sequence. Where does it start? N is 0, right? N is 0, that's when your unit step sequence will be defined. And as n increases, you are going to have some finite values. And if you were able, if you wanted to sketch this, what would you get? Well, you'd get something here, then you'd get here, then you get here, then you get here, right? 1, you get 1/4. Half, you get, hold on. When that becomes 2, oh yeah, I did it right. It's going to go smaller, right? 1/4, 1/16, 1/, whatever. All right, next. It's going to be only for that. X of n. The input is also given, half raised to n, u of n, also expressed in the form of step sequence. So you have some input, exponentially decaying, and you also have some h of n, exponentially decaying. You are going to try to find the output of this. So let me sort of step back here and talk about what are we given. We are given the impulse response, right? So let me, before, after. The system is where? The system is here. What are we given? The impulse response. H of n is 1/4 raised to n u of n, right? And then we are trying to find the output when the input is half raised to n u of n. That's our problem, right? But let me ask you an interesting question here. Not so interesting, actually. Let me ask you a simple question here. We have the same system. What is that? For this same system, what is the output here? That's it. It is h of n. Input, impulse response, right? So this is the way we have characterized the system. Then we said, all right, I know everything about the system. H of n moved there, characterized it. Now we can find the output for any new input, right? You guys see how h of n plays a role? H of n is an output of the same system to which the input is delta, impulse response. Once we know the impulse response, then we can use that to compute the output for any new arbitrary input. All right, let's go back here. Let's try to do this. The system is linear time invariant, so that means that we can compute the convolution, right? Because superposition is going to apply. And here is a good news. Convolution is commutative. So x convolved with h is the same as h convolved with x. Why is this useful? Because whenever you are trying to do convolution, there are a few steps involved. One is flipping of one signal about the y-axis. And then after you flip it, you will move it across the first signal. And every time you move, you will multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, and so on to get your output elements. Which means if it is commutative, you can choose the one that stays and you can choose the one that flips and moves. One might be working out much better, easier mathematically than the other. So you got to see it, right? Like a few steps ahead. All right, how is this going to work out? So I'll give you guys more examples about that. But that's where you can leverage that commutative property. All right, let's go into this. Y of n is what? That's your formula for discrete convolution. X of m multiplied by h of n minus m. M goes from negative infinity to infinity, right? Which is simply x convolved with h. Just to differentiate between the signals, I have one in blue and one in red. So to explain this, let us start with this toy example. What is this toy example? N is 5. How are you computing n is 5? Well, just substitute n is 5 in all of this guy. What happens then? Well, y of 5, the fifth element, right? When n is 5, when time is 5, the output is the summation of m goes from negative infinity to infinity, x of m, can't do anything about that, h, the impulse response, gets flipped and shifted, right? Flipped and shifted. So I need to run through that. Let's try to run through this. Mathematically, it's going to be pretty easy to run through that because of the presence of u of m's and u of n's. So let's see. Y of n, we are still computing just one element in the output. How many elements are there in the output? Many. In fact, I can tell you how many elements are going to be there. There are going to be infinite elements. And if you know the bounds of input and impulse response, and if you know the bound, there are going to be 2 bounds, right? When is x of n starting? Let me go back here. Let's take a look at here. When does this start and end? When does this start and end? Question mark. What was that? Okay, when does it end? 0 infinity? Yeah, how about this? Same. For the output, it is going to be sum of the lower limits plus 2 sum of the upper limits. 0 plus 0, 0. Infinity, infinity, infinity. So it's going to start at 0, it's going to end at infinity. So right away you know where the output is going to lie. So with the limits of the signals that you're convolving, you right away know the limits of the output signal. And this applies even for continuous time. Same way. All right, let's talk about another thing here. If you have, say, LKMNO, which letters should I use? Let's use A and B. All right, so this guy if this guy has A elements, I'm talking about non-zero elements, right? 1, 2, 3, something like that. If this guy has A elements and this guy has B elements, then the answer is going to have A plus B minus 1 elements. Right now, just write it down. When we look at an example, you will see how this can be useful and whether it is correct or not. We'll also look at that. So you now know the properties for starting and finishing and the number of elements between that start and finish. All right, let's go back here. We are doing this, right? So if you're trying to run through this, what do you have? X of m is going to be what? I know x of n. I'll simply substitute m for n, and I get that. Yeah? How about this? Well, I had h of n. Instead of n, I will put 5 minus m, and I get that, right? I just made changes over here and here. I've replaced n with 5 minus m. Next. I'm going to try to solve this summation here. But before I do that, I'm going to leverage the presence of these unit step functions. U of m, can I say that it is going to be 0 for m less than 0? I can say that, right? Step sequence, when m is negative, u of m is going to be 0. All right, so that takes care of my lower limit. How about this guy? U of 5 minus m. It is going to be 0 when m is greater than 5. Why? Put any number greater than 5. What do you get? 6, u of negative 1. 7, u of negative 2, and so on. All of those are 0. Yeah? So can I say that u of m minus 5 for m greater than 5 is going to be 0? You guys agree with that? Now, let us suppose you don't want to agree with this without a sketch. How do you look at it in terms of a sketch? Well, this is going to be your u of m, right? Yeah, this is m, this is u of m. I need what? I need u of 5 minus m, right? How is that going to look like? Let's try to find u of minus m. Can I say that u of minus m is simply going to be this? Yeah, just flipped. Yeah, okay. I need to add 5. When I add 5, I go this way or this way? All right. Right. This one is going to be 5. Any m greater than 5 is going to be 0. Right. So this is what? U of 5 minus m. Right. You see, nothing here. Right. All right. So using that, I've got this guy for help with lower limit. I've got this for help with upper limit. And based on that, I've adjusted the lower limit and upper limit of the summation. I still have these two guys carrying over. So I have this guy carrying over here, and I have this guy carrying over here. I need to get rid of the u of m's because those are just ones, right? No need to include that anymore. Next. Simplify. I've got half raised to m, and I've got 1 over 4 raised to 5 minus m. When you simplify this, what are you going to get? Well, I can pull out the 1 over 4 raised to 5 outside the summation. Doesn't depend on m. What am I left with? I'm left with half raised to m and 1/4 raised to negative m. So my claim is it is going to be 2 raised to m. How is that? Well, the first piece is 2 raised to negative m, and the second piece is what? 2 raised to 2m. Right? 1 over 2 raised to 2, the whole thing raised to negative m, 2 raised to 2m. Multiply that, you get 2 raised to m. So I have 1 over 4 raised to 5 summation for m from 0 to 5, 2 raised to m. All right, so this I think requires us requires some identities, right? Some power series formulae to deal with this, and we have that on the next slide. Questions about this? 1, 2, go ahead. Oh, just an example, because next I'm going to say, all right, 5, it works out this way, n, it is going to work out how, right? Oh, right, exactly. So we are just going to adjust our upper boundary to n instead of 5. But that's next. All right, so here we have got 2 raised to m. So we are going to need some formula, and we'll get there. So what are we doing next? Nobu has pointed that out already. Why did you take 5? I actually wanted to do n, right? Y of n, the output. So what am I going to do? I'm simply going to adjust. Earlier, I was having 5 here and 5 here, right? Now I'm going to have the general case, n there and there. So how are things going to change? This is going to remain as is, my lower limit of the summation. But over here, I've got the upper limit of the summation now until n instead of 5 earlier. Yeah, same plot, except it is stopping at n instead of 5. Substitute, solve, you get this. 1/4 raised to n instead of 1/4 raised to 5. Summation goes from 0 to n instead of 0 to 5, 2 raised to m. Once I evaluate this summation, I'm going to have a function in small n that is going to be the output, y of n. Now I'm looking at Google's, please tell me how do you add a power series, right? Instead of that, instead of Googling it, because half of the people over here don't have laptops, I'm just providing this as a slide that you guys can refer to. And yes, this is going to be part of your crib sheet given in the exam. Always has been and is also going to be. All right. For any x, real or complex number, if I have summation I starting from 0 to n, then I can write that using this power series over here. When I have the magnitude of x less than 1, like half or 1/4, which is the case I have right now, then it will go to 1 over 1 minus x. Something that I remember is half, right? When x is half, it will be 1 plus half plus 1/4 and so on. It will tend to 2, right? You guys remember that? So that's coming from that identity there, 1 over 1 minus x. However, if you have something like this, I times x raised to I. Again, magnitude of x is less than 1, then you can use x divided by 1 minus x whole squared. So these are 3 power series formulas that you need to access, then you need to have as a reference in order to solve those earlier steps, right? So for example, for us, what are we going to use? We are going to use something like this, right? Y of n had what? 0 to n, 2 raised to 5, or 2 raised to n. We had 2 raised to m earlier. So we can use this, express our answer in this way for this guy, and you're done. What are you going to need to do after that? There's one more step that is missing here. You have 1/4 raised to n, that stays. This summation can be solved by using this, but there is one more step remaining, which is you still need to multiply by u of n at the end, because it is only going to be valid for n greater than or equal to 0. Because we know we have set the limits 0 to infinity for the output. All right, questions about this example? Computing analytically means evaluate the summation using the power series equations that you have. 1, 2, 3, next. Calculator to calculate that part? And now you're asking really tough questions. Sure, you can do that for homework, but if you are asked something like this on an exam, then I would expect to see some work. Because over here, what is the thing that you would pay attention to? The limits of the summation, right? And the fact that you need to multiply by u of n. I'm sure that your calculator gives you all the things, but it is not going to give you the u of n multiplication at the end. So some of the details you're going to have to sort of add at the end. Here, you can do this for homework. Don't do this for exams. That's where I'll leave it at. Let's see. Next, we have discrete convolution using the array algorithm. And whenever I present array algorithm, students are like, oh yeah, this is so easy. Why? It's because it's very systematic. And all it needs you to do is multiply numbers and add them up. So pretty cool. What do you have here? You have X and H. What are they? Those are elements in the input as well as elements in the impulse response. Quick question. Why didn't we do this for the previous example? 1 over 4 raised to n u of n. Why didn't we do this? All right. Our array algorithm would be like we would turn 45 and we would still be writing our algorithm, right? It's never going to end. So that's why I'm saying array algorithm works really well when you have finite number of elements in your input and impulse response. So you've got x of 0, x of 1, 2, 3, 4, right? So you have got 5 elements on the input distributed on the top here, and then 5 elements of the impulse response, h of 0 all the way down to h of 4. And what have you done? You have evaluated each element in this array as multiplication of this guy, and this guy goes over here, and so on, right? So multiplication of these two goes over there, those two goes over there, those two goes over there, and so on, right? So you've essentially multiplied the two things and you have put in the products over there. Once you do that, what are you going to do? You're going to evaluate the sum along the diagonals. So for example, this sum will give you y. So this, when you sum it up, you are going to get y of 0. Question, why are you going to get y of 0? 0 plus 0, you get 0. So you add the indices of input and your impulse response to get the index for the output. In other words, if your input started at -1, -2, and your impulse response started at 2, 3, 4, all you would need to do is add those indices to get the index for your output. That's it. But what are you doing? You're essentially saying, oh, hold on. Yeah, that's right. So y of 0 in this case is what? Only one element, the product of x of 0 and h of 0. Next, the summation of this 0 with 1 and 1 with 0, that is going to give you y of 1. Now here, how many elements are you going to have? Y of 2, 3, 4, 5, 6, 7, 8. Tell me, what is the lower limit of your response? 0. Upper limit, 8. 0 plus 0, 4 plus 4. Yeah? How many elements are there? A plus B minus 1, right? 5 plus 5 minus 1, 9, 0 to 8. You guys see that? Yeah? Good. There would be some numbers missing. But there's no 5 by 3 because our elements are starting at 0. Right? So 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. We are using all of those in this. Am I not understanding your question properly? Yeah. So is your question about what would happen if your elements in the middle are 0? No. Give me an example. Like input is how many elements? 5 elements of array. Yes. Oh no. No, it would not be zeros, right? Anything less than 0 is a 0. Anything above 8 is a 0. You wouldn't even run the array for that. The array would only apply for the values that are within the bounds. Some elements within the bounds may be 0, right? It could go 1, 0, 1. So it may be 0, and you will include that. But outside the bounds, you don't include that in the array. Good. Oh, yes. It is as simple as multiplying two polynomials. The polynomial coefficients are these numbers. When you multiply the two polynomials, you will get a higher order polynomial whose coefficients are those. So array algorithm is as simple as polynomial multiplication, which is why it's very easy, right? All right. Questions about how do you run this array algorithm? How do you deal with signals that could start with -1 and so on? All right, let's try to run some exact numbers here. You are given a sequence for input. You are given a sequence for the impulse response. One in blue, one in red. Input is the blue, which is represented over here. Impulse response is the red, which is represented over here. All I've done is I've multiplied 1, -1, put the element here. So I've already multiplied and given you numbers as the first step. I just thought I will help you out with this very difficult math problem. Then let's try to do this. All you're doing is summations, right? Summation here, summation here. Next, what do you get for the first one? Y of what? 0 plus 0. What is that going to be? -1. Yeah. Next, y of 1 equals -2. Y of 2 equals, let's see, 3. Y of 3 equals 9 minus 6, 3. Then y of 4, 6, 8. Y of 5, -9 plus 6. Y of 6, 17, 13, 7, -16, 8, 4. All right. Easily be computed. Finite elements, if you have them, just plug them in and you're done. These could be numbers, and in some cases, these could be constants, right? So in some problem, we could be talking about A, B, C, or A1, A2, A3, and so on. And if you're asked to find out the convolution result, then you could, instead of putting in some constants, you could put in some variables in there instead and work the same way. All right, questions about the array algorithm to compute discrete convolution? Some of you may like Matlab. For those of you who like Matlab, let me give you guys a sort of a incentive. Discrete convolution in Matlab. How can you do it? Using just one function. Define h, define x. So I've defined over here. This is in Matlab, and this is command prompt, right? That's where you are writing your functions. X is 211. H is 123. CONV is a command in Matlab that allows you to do this discrete convolution. So y is convolution x comma h. right away you get all those elements in Y. And when you actually want to view the signals, then you can use the stem command to plot them out. Why am I using stem and not plot? Plot is applicable for continuous time signals because it will connect the dots, right? Over here, you want them to be just samples because you're talking about discrete convolution. So instead of plot, I'm using stem. On the x-axis, I have 0 through 4, which is sort of 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5 elements. Why did I use 0 to 5? 0 to 4? 0 plus 0, 0. 2 plus 2, 4. Right? 0, 1, 2, 0, 1, 2. The times at which those values are there. Stem 0 to 4, y, you will be able to look at your result. So a quick and easy way to validate your work by hand. Where were we? We did this. I'm going to switch screens here so that we all can look at this. So let's see, share something else, share my screen. Yes, I want you to stop that. All right, so hopefully you guys are all able to see my screen. Yes. People are online are able to see my screen. All right, so this is your third way of executing the graphical discrete convolution. This is the graphical method. And if you understand this really well, your understanding of the continuous time convolution will go really, it'll be easy for you to understand that as well. So what are we doing here? Think about it in step and step, right? So here, look at this. What are you trying to find? You're trying to find this convolution. There's a X input, there's a H impulse response, and you're trying to run through this convolution. Now try to zone in on this particular summation here. If you are given X of n, see over here on the left in the blue, you're given X of n. What do you want? You want X of m. How do you go from X of n to X of m? N to m, what do you need to do? If I wanted X of m here, and I'm running the summation with respect to m, which also means that I want this to be m. I want this to be m, and I want this to be m. What should I change? Just replace n with m, right? For here as well as for here. How about this guy? Oh, I have a few more steps involved here. First is h of n minus m. So I need to do a few things here. First, I need to go from n to m. Nancy to Mary, right? Next, once I get m, I need to flip it about the y-axis so that I get h of minus m. And then I need to add n to it. You guys see that? N to m, flip it, add n to everything. Yeah? All right, so let's do the first step first. X of m, m. No problem. We just changed that. We got this now, right? Next. H of n became h of m, just as we changed x of m. You guys okay with h of m? There is a reason why I have put a color gradient on h. Why is that? Because when I flip it, you guys should see which element is going where after the flip. What do you guys think? Well, when you flip it, the darker is going to go all the way to the outward, right? -4, right? That's your h of n minus m. So far, so good? Once you have h of n minus m, you are adding n to it. I think of adding n to it as putting the elements of h on skates so that they can move from -infinity to infinity. As simple as that. So what is going to happen? When you add n to it, what do you think happens to this? 0, -1, -2, -3, -4. What do you think happens to that when you add n to it? They all get added by n, right? N minus m, n here, n minus 1 here, n minus 2 here, n minus 3 here, n minus 4 here. Earlier, it was at -1, -2, -3. It was static. It was not moving. Now, it is sort of on a scale now. You can move now because you can change n. You want y of 1, put n as 1 here, multiply them, add the result up, and you get it. Are you guys okay with this so far? All right, so what have we done here? We have graphically represented x of m here and graphically represented x of h of n minus m here, right? Now what do we need to do? We need to evaluate this summation. And what are you doing with the summation? You're multiplying the two signals and you're adding up all the elements after multiplication. So tell me, if n is 0, what will the summation give you? If n is 0. 1, right? Because there will only be one element that will be overlapping, the one on the y-axis, right? So it will be 1 times 1, that's it. Everything else will cancel out, and you will get 1 for n is 0. How about n is -1? If n is -1, will you get any overlap? Was that? Oh, -1. -1, meaning it's moving to the left. 0, right? So if n is -1, you don't get any overlap, so you get 0. If n is 0, you get 1. What about n is 2? Oh, sorry, n is 1, right? If n is 1, you get 1 times 1 plus 1 times 1, 2. Increases, right? 1 plus 1 or 1 plus 1 plus 1 plus 1. It's going to increase linearly. Can I say that? For how many elements is it going to increase? Oh, well, here, let me ask you this. What would be the maximum value? One guy has 4 ones, the other guy has 5 ones. What would be the peak value? 4. Because 4, so here, focus on my fingers here. 4 elements here, 5 elements here, right? So this can be your maximum as well as this, right? So you're going to get a trapezoid shape. Can I say that? Increases linearly. It's going to be at the maximum for 2 samples, and then it's going to decrease linearly as it exits away. Is that seeing that? So it's going to be 0 for n less than 0. It's going to be 1, 2, 3, 4, 4, 3, 2, 1, 0. Yeah? And it's a trapezoid shape. Why? Because the signals are different in terms of their lengths. If x and h were both the same height and the same width, you would get a triangle. Are you guys seeing that? So as you are changing n, here, the last piece of animation, as you're changing n, you're doing that. You're moving this guy across the other guy. This is fixed. X is fixed. And as you're moving, by the way, you're moving not in a continuous fashion, you're moving discrete, right? 1, 1, 1, 1, 1. And as you're moving, you are multiplying the overlapping elements and you're adding up the results. Questions? Easy, difficult? Where are we at? Huh? All right, so let me continue our discussion with the slides. Where are they? They are right here. I need to do what? I need to do share, All right, so animation was because it would have appeared this way otherwise. Let's see. Let's come back here and continue. All those steps are sort of broken down in these things. So for example, h of -1 minus m, x is here. It is fixed. No overlap between these two guys. So you get an output of 0. That is for what? That is for y of -1. It is consistent with my claim that you need to get, when you add up the lower bounds, you get the lower bound of the output. It is consistent with that, right? 0 plus 0 starts at 0, ends at what? Ends at 3. Let me go back here. Ends at 3 plus 4 and should end at 7. Let's look at how it is moving. H is moving from left to right, and as it is moving, n is changing. -1 here, 0 here, 1 here. Oh, wait a second. Oh, 1 over here for this. Then 2, 3, 4, 5, 6, 7. It's exiting, right? At each move, you are finding out the common elements. So for example, over here, no overlap. For next guy, this is the overlap. For next guy, this is the overlap. 3 elements are overlapping. 4 elements are overlapping. Next, 4 elements are overlapping. One guy already exited out, right? There's nothing here. And then back. 1, 2, 3, 2, and 1, and after that, zeros. You guys see the trapezoid shape in your mind? Yeah, you're able to see it graphically. Do I need to show all these things graphically when you ask me to do this convolution? No. Why is this necessary? Because it is going to be helpful when you go into continuous time convolution. If you understand this, that will be easier. Whenever you look at discrete convolution, you will be asked to generally do analytical computation or array computation. You will not be required to do graphical convolution like we did. It is more for understanding purposes. And even if I give you graphical convolution, it will be for a very, very small number of steps, anyway, elements. Next, see, you got that rectangle, a different side is a rectangle. The output evaluated to be that way, right? So let's talk about the first thing. Let's talk about one thing that you will hear multiple times with convolution. Rectangle convolved with another rectangle. This is a rectangle sequences, right? Rectangle convolved with rectangle can either be a triangle or a trapezoid. If those rectangles are exactly the same length, then you get a triangle. Maps, when it maps, you get a peak and then you go down, right? So when you see a trapezoid as a result, and if one of the inputs is a rectangle, you know the other input is also a rectangle. And you can do other things with this. You see, where is this coming from? 3 and 4. That is essentially coming from this guy and this guy, right? When it is shifting, after 3 moves, that's when you get your first peak. After 4th move, you get your second peak. And then it goes down. So we have also sort of put in these guys. These are zeros, but you have put in over there just to show that it is going to have a trapezoid-like shape. So in other words, if these were continuous pulses, your output would have been a trapezoid, continuous. Questions here? We are summarizing the steps that we looked at over here in terms of graphical convolution. The first step that we did was plot the signal x of m with respect to m. Second one was plot h of n minus m. And h of n minus 1 was also sketched with respect to m. Why are signals being sketched with respect to m? Because our summation is running with respect to m. When you're doing that multiplication and addition, it is with respect to m. So that's why you have versus m here, versus m here. So when you went for h of n minus m, you actually did h of m first, then flipped it, and then you put it on a rail so that it can move from negative infinity to infinity. Next, as you're sliding this guy across the input in integer time steps, you're doing two things. One, multiplying all the overlapping elements and then accumulating their results. Multiplying the overlapping elements and adding them up. What do you think this will be? When you go for continuous convolution, how do you think this will change in terms of the last statement? Multiplying the elements and adding them up. What do you think that will change to? Go ahead. Okay, the summation will become integration. What about the other one? So, go ahead. Multiply the functions, right? Multiply the functions and then integrate over that period, right? Over which they are non-zero. Excited? Let's get into it then. So continuous time by the way, continuous time convolution happens to be one of the tedious components of this class. In Coco, you remember K-maps very fondly, right? Oh yeah, I love K-maps. Convolution for many is something that goes the other way. Oh, you're doing convolution right now? Oh my gosh, so sorry for you. So let's try to make this conversation about continuous time convolution as engaging as possible. I don't mind spending 2 lectures on this because I want you guys to sort of get each and every aspect of continuous time convolution. All right. How do you deal with continuous time convolution? Well, all our deltas are going to change to delta of t's, right? Delta of n's are going to change to delta of t's. My goal will be to do the same thing. Characterize the LTI system, ask its name. And then once I know its characteristics, then I can evaluate the output of that particular system for any new input that you give me. So let's try to do this. Input is an impulse, output is h of t, the impulse response. I have characterized the system in step number 1. I know the LTI system now. Once I know the system, then because I know this, right? I know h of t here. I'm using it there. Now, once I know that, for any new x of t that you give me, that new x of t could be arbitrary, right? It could be a step, it could be a ramp, it could be a combination of steps, could be combination of ramps, combination of impulses, whatever. Oh, by the way, let's do this. All right, fine. Let's. If my input is delta of t, my output is say u of t minus 1. Just as an example. What would be the output here if the input is 2 delta of t minus 1 plus 3 delta of t minus 3? Agree? What property did I use? And time invariance is taking care of the -1 to -2 and so on. And linearity, LTI systems, right? So I used superposition essentially. Alpha 1, t minus t1, alpha 2, t minus t2, and so on. So Why is this necessary? Because this. On your homeworks, you will see some problems can easily be solved by breaking up the input into smaller inputs and then evaluating the output for this guy plus this guy plus this guy. Essentially using superposition to find the output. Or you can say, I am brave. I know continuous time convolution. I'm going to take this guy and I'm going to integrate the hell out of this. You are going to get the answer, maybe the right one, but you would have had some stressful time in the middle. So I want you guys to take an easier approach, superposition, wherever you can. Let's see. Let's go. You guys agree with that, right? For this input, you got that output. And for this input, you got that output. Because you were given the first statement there. All right, let's see. Once I have characterized the system h of t, I have this new input x. I can find the output by simply doing x of t asterisk h of t, which is going to equal, let me not say equal, well, I can say it, then I can prove it. All right. X of tau h of t minus tau d tau. Look at this. Summation m equals negative infinity to infinity, x of m, h of n minus m. Yeah? Integration negative infinity to infinity with respect to tau, x of tau, h of t minus tau, d tau. Right? You see that one-to-one mapping there? N to t, m to tau. Summation became integration. This is my claim. I still need to prove this. But since I'm claiming things, I will also claim some other thing. Commutative. Convolution is commutative. So x convolve with h, same as h convolve with x. So I've written the other over here. And I'm going to also prove the commutative property later on. Now, my first goal is going to be to prove whether the output of this system when input is x is this or not. To that end, let me go through a series of steps. The first thing is, what is the output when the input is x of t? That's my goal. Find out what y of t is going to be. So the first thing that I'm going to do, give it an input of impulse, find the output as the impulse response, h of t. Next, if I multiply the input by k is a scalar, because of homogeneity, I will also multiply the output by the same amount. What was this? I will yell twice as loud and you guys will get hurt twice as much. Right? K for the input, output k times bigger. Next, k remains as is. I'm shifting the input by tau. If you shift the input by tau, the output also gets shifted by the same amount. Why? LTI system. Subset TI system. Time invariance should apply. Delay the input, delay the output also by the same amount. So a tau over there corresponds to tau over there. Next is sort of a sleight of hand, right? K is x of tau. Why is that okay? Why did you choose x of tau? K was a scalar. Is x of tau a scalar? Why not? X of tau is what? Tau is some arbitrary time. So evaluate the input at this time, tau, 1 second, 2 seconds, whatever, and it will give you a constant, right? It's going to be a value of x of tau. No matter what kind of signal it is, real or complex, it is going to give you a value at that time, tau, right? I'm not saying the whole function, I'm just saying the value at tau. I'm treating tau as one time, not a variable, independent variable. So k becomes x of tau. This guy remains as is, x of tau multiplied by h of t minus tau. One is for homogeneity, the other is for time invariance. Next, integrate both sides. In other words, accumulate all the inputs and you accumulate all the outputs. So when you accumulate all the inputs, what do you get? X of tau, delta of t minus tau d tau. What is that? The whole class emphatically says x of t. X of t, that's it. Take the signal, multiply impulse there, impulse there, impulse there, impulse there, impulse there. The whole function is being tracked, right? That's the sampling property. What is at the output? If x of t is the input, then we would have probably found y of t to be this. Integration x of tau, h of t minus tau, d tau. Hence my claim. Or not this. This. Okay. So that's your convolution integral. How are we doing on time? All right, you guys mind hanging around with me, hanging with me for a few more minutes? Yeah. The 11 minutes of financial conversation is hurting me a bit now. All right. It is. But I also need to be on the ground. All right, let's see. I would happily make one homework just be that, you know. That's what I want. No. I'm not going to get into put that. If I get into that, then our class turns into right. So it's going to be a lot of pain for me and regret. So I'm not going to go there. But it's something else. Yes. All right. Let's see. This integral is called the convolution integral, and you're doing it for input and impulse response, x and h, denoted by that asterisk operation. Next, we can do this two ways. Don't have an array algorithm. Why don't we have an array algorithm for this guy? X of 1.1, x of 1.111. You guys see that? We don't have a finite number of values. We have a continuous time function. So we don't have an array algorithm for this, unfortunately. However, if you are so inclined towards using the array algorithm, this is what you can still do. You can pick out some values of this continuous time function, put it through the array algorithm to get a general shape of the output. Right? You will not get all the values, but you can get sort of a shape. So you can still get some idea there. All right. On that same topic, can I do continuous time convolution in Matlab? What would I need to do? Hold up. Who's that? Whoever. All right. Over here, I am doing a discrete convolution. Multiply functions. Let's suppose that these, instead of saying 2, 1, 1, instead of them being values, it was actually 2 as unit step, 1 as unit step, 1 as unit step. Here is the idea. In Matlab, it's a computer, so it understands samples. It's a discrete device, right? So instead of samples being 1 second away, first sample, second sample, third sample, what you can do is you can assume the time between samples to be very, very, very small. TS, 1 millisecond, right? So instead of, so you can get it's the same convolution of operation, but you are, instead of, when you say 0 to 4, the step is what? 1, right? 0, 1, 2, 3, 4. Instead of that, you say 0 to 4 in steps of 1 millisecond. Then you get what the continuous time convolution is going to look like. So it's a way to approximate that, not evaluate that. All right, let's come back to not this, this. Compute it analytically. Compute it analytically essentially means evaluate this integration. And it's going to work when you have signals that have a defined lower and upper limit, but graphically works for all. The first one is what? Analytical approach. So let's put these things into the convolution integral and find it out. Y of t, integration. X of tau. What is x of tau? Tau, u of tau. That is x of tau. H of t minus tau. Oh, hold up. This needs to be h. T minus tau, u of t minus tau, d tau, negative infinity, infinity. All right. Please check if you guys agree with this or not. Yeah? Okay, next. Because of u of tau and u of t minus tau, can you guys tell me how are the limits of the integration going to change? What is the lower limit going to be? 0 because of u of tau. What is the upper limit going to be? Tau because of u of t minus tau. What do you have left? Tau is left, multiplied by 1, multiplied by t minus tau, multiplied by 1, multiplied by d tau. Yeah? I think this integration, you guys can do it pretty easily. T tau d tau 0 tau minus tau squared d tau. T multiplied by what? It is tau for tau seconds, right? And you are integrating it. So what is that going to be? Tau squared divided by 2. Is that okay? Half times t times tau squared. Oh, hold on. I did something wrong here. Oh, this is t. That is t. That is t. What else is t? No, he agreed on the. Yes. All right. So now it's okay. So you've got, let's see, tau d tau. I think we are missing something here. Yeah, so 0 to this is fine. Next we have what? T tau 0 to t minus tau squared 0 to t. So if I integrate out tau, I'm left with t, right? So I've got t multiplied by, I'm integrating tau, so I get tau squared divided by 2. All right, then minus, what do I have? This is 0 t minus, all right, that's good. This is going to be what? T squared divided by 2 minus 0 minus t cubed divided by 3. What is that? Is that okay? I think we need to do one more thing. starts at 0, ends at infinity for both input and impulse response. So the same thing applies for the output as well. All right, t cubed divided by 6 u of t. Questions with this example? Going once, going twice, and done. Next. This is going to be our last example for the class today, but it is also going to be a very an example in which you get to experience a few details. So I want you guys to sort of pay attention to those details. If you understand this really, really well, then you understand most of the continuous time convolution really well. So here, what are we trying to do? We are trying to convolve f of t with g of t. One is a rectangle and one is a sawtooth. They are not periodic waveforms. They don't go on forever. They are just limited in time. So how am I going to get this convolution done? I want you guys to think about this first. Which signal is it going? Which signal are you going to choose as stay the same, flip and shift? Which signal are you going to choose to stay as is and the one that moves? Go ahead. Nice. Why is that? Doesn't change, right? More importantly, if this was the equation of the line, and when you do t minus tau, then you have a lot of t minus taus to take care of in the integration. Or if you have something like this, it's just a constant. So when you have a constant, you can more or less pull it out of the integration, right? So you guys need to sort of think one step ahead. If I choose this function versus that, how are my integration steps going to be? All right, so what are we doing? We have plot, those are my steps. Plot g of tau, plot f of t minus tau, then multiply the two signals. And after you multiply the two signals, wherever that common sort of area is, not area, I shouldn't say area. After you multiply the two signals, you integrate over the time they overlapped on. You guys good? All right. So I have f of t, I have g of t, right? So can you guys help me plot g of tau? It's going to be the same thing, right? Going up from 0 to 1. Let's do blue and straight. What is this going to be? Tau. What is that going to be? G of tau. This is going to be what? 1, 3. Can somebody help me find the equation of this line? 1/3. So forget about the use. Just the. That's it. Oh, let's forget about the use. Just the equation of that line. Because the limits, I will take care of them during the integration process by adjusting the limits. So that's tau divided by 3, right? Yeah. Next, what do I have? F of t minus tau. If you guys have zoned down, phased out a bit, I want you guys to be on now. On now. How are we plotting f of t minus tau? F of t is this. A rectangle between -1 and 1 with a height of 1. What is f of t minus tau? F of tau is going to be the same thing, right? So for f of tau, I don't have to struggle. I can just say, all right, tau, tau, done. What is f of minus tau going to be? F of minus tau. The same. Flip it about the y-axis. Well, it is symmetric about the y-axis, so when you flip it, it's the same, right? Done. What is going to happen when you add t to it? You see that? It's like it was constant, now it is on a rail. Now it can move as t changes. All right, so let's sort of plot that out over here. We had a rectangle, and just so you guys see that it is on a rail, I am not going to plot it in the middle. In fact, I'm going to plot it over here, because it's depending on t, right? Small t. That t could be big, small, doesn't have to be 0. Next, what is this? This is, I think it was t, where was it? T plus 1? Yes. Tau, f of t minus tau. The limits are in t, but the axis is in tau. Axis is in tau because we are integrating with respect to tau. Okay. Are you guys okay with sketching g of tau and f of t minus tau? Yeah? Next. I want you guys to answer this. Case 1. Y of t equals question mark for t plus 1 less than 0. Think about this. T plus 1 less than 0. What am I comparing with what? T plus 1 less than 0. When t plus 1 is less than 0, what is output? Why? 0. No overlap. You guys see that? So far, so good? So that was case 1. I don't need to talk about case 1, we already did. Next, as t plus 1 increases, what is going to happen? Okay, there is going to be overlap. How is that overlap going to look like? So let's start doing that. So in case 2, right? In case 2, let's put it in. G of tau is over here. And now you are saying that it is going to accumulate, right? Something like this. This is what? T plus 1. What is this? This is t minus 1. This is 0. This is 3. Yeah? The place where it is sort of overlapping is right here. We have to find two things here. One is easy, one is difficult. The easy thing is the integration. The difficult thing is the range for time for that case 2. The first one was easy. T plus 1 less than 0, right? How about this? T plus 1 and 0. Obviously, over here, t plus 1 should be greater than 0. How about the other side? What would be the last point? As this rectangle is moving into the triangle, what would be the last time for which you are still multiplying the same two signals? When what overlaps with what? Go ahead. T minus 1 overlaps with what? If t minus 1 overlaps with, that is not going to happen soon, because this guy is 2 seconds. This guy is 3 seconds. So there is going to be a time where the whole rectangle is traveling inside the triangle. So then the limits of the integration are going to be different. I'm talking about the limits of the integration which will start from here. What would be the last sort of time there? Can I say that that is going to be when t minus 1 meets 0? Can I say that? The edge meets that. Okay, so what was the first thing? That was t plus 1 has to be greater than 0. What was the other thing? T minus 1 has to be less than 0, right? If you combine these two, what do you get for t? T has to be between what and what? Yeah. For -1, between -1 and 1, -1 and 1? Cannot be -1 and 1. What was case 0? Oh, yeah. This was what? This was t less than -1. Yeah, that was t less than -1. And then this is between -1 and 1. Yes, that's the next one. Okay, what is the limits going to be? Y of t equals. What is the limits? All right, this should be easy, you guys. Where are we multiplying the signals? The lower limit is what? Upper limit is what? What are we integrating? There you go. What do you get? Tau squared divided by 236, limits t plus 1 and 0. What do you get there? T plus 1 whole squared divided by 6. That is going to be the function y of t between what and what? Between -1 and 1. Questions here? You see how we have computed the lower limit of integration, upper limit of integration, and it was what? Multiplication of the two. This guy was 1, this guy was tau over 3. Multiply the 2, you get tau over 3. Go ahead. Because you see, as this guy is moving in, so you see, over here, there was no overlap. And once this guy overlapped, you see, where are you integrating? 0 to something, 0 to something, 0 to something. Right? And it is going to continue until the rectangle is completely inside that triangle. And when it is, we are going to deal with what? Case 3. Now let's talk about case 3. Stay with me, guys. Stay with me. It's going to look something like this. Pardon the scale of this, because 1 is 2, 1 is 3. So they're just, one is smaller than the other. Tell me, what are the integration limits now? Oh, wait. Right? Yeah? Now, here, what are the limits on the t? Range of t? One to 3. So here, this guy is what? T plus 1, right? This guy is 3. So can I say that the lower end was plus 1? Why? Because we had already computed there. So lower end is 1. The upper end is what? T plus 1 less than 3, right? So that is like saying t is less than 2, right? So this is what? This is between 1 and 2. Between time 1 and 2, the output y of t is all of that. So what is that? This is tau squared divided by 6. The limits are t plus 1 and t minus 1. I'll let you guys do that. All right, fine. T plus 1 squared 6 minus t minus 1 squared 6. Right? So for this, you got that. And I'm sure you can simplify it a little bit more than that. Questions here? Case 4. What is going to happen next? That rectangle is going to exit out of the triangle, right? What are the limits going to be here? T minus 1 and 3. Until when this is until when is this going to continue? T minus 1 less than 3, right? The lower limit was 2, the upper limit is going to be this. This means what? T is less than 4. So 2 to 4, it does that. Because 2, it stopped there, right? What is it going to do? Y of t is integration t minus 1 to 3 tau divided by 3 d tau. Again, you guys can do the integration, substitute the limits, find a function in t. What is after that? 0. All right, so this guy is going to be here, this guy is going to be here. So what is that going to correspond to? T, this is what? T, this is t minus 1, right? T minus 1 is greater than what? 3, right? So that implies what? T greater than 4, y of t is 0. No overlap. Zero, then some quadratic, some other quadratic, some other quadratic, 0. We evaluated the output for time greater than 4, we got 0. For time between 2 and 4, we got something that needs to be solved. For time between 1 and 2, you got that. For time between -1 and 1, you got that. And then for less than 1, you got no overlap, 0. Now, I want you guys to note a few things here. One, without even doing any of the math, I could have told you that the things start with -1 and stop at 4. -1 plus 0, -1. 1 plus 3, 4. So the answer y of t would have started at -1 and ended with 4. -1, less than -1, it was no overlap. Only when you had more than -1, you got something. And you had nothing after 4. You guys see that? So that addition of the lower limits and addition of the upper limits works for this. Why is this useful? Sometimes you are doing the math and you get some absurd result. You know, one very quick check. Look at the bounds on the inputs and output. Look at the bounds of input signals, the signals that you're convolving. Look, and you have an expectation for the bounds for the output. Question here, what part of this was difficult? I know the answer to that question. I just want you guys to recognize that as well. Integration was, well, not that difficult. What was difficult about this? Bounds, right? Even the integration limits was not difficult because that was just like, okay, this limit to that limit, that limit to that limit. But bounds, how are you separating the t? -1 to 1 and then 1 to 2, and how did we break that up? So let's talk about that for a minute. How are you going to recognize, so what is going to be your basis? These signals are going to keep changing as you do the convolutions. So how are you going to go about finding the bounds for the times? What should be consistent for a given time? Say negative, so here, think about this, 1 and 2, right? Why did we choose 1 and 2 for this? Because that is the time for which the signals that you are multiplying, they are not going to change, and the limits for the integration, they are not going to change. Between time 1 and 2, those three things are going to be the same. The functions multiplied, the lower limit, and the upper limit. So the moment any one of those three things change, you need to have another range for it. Guys see that? Yeah? Here is a homework for you. Go to Wikipedia, type in convolution. There are some nice animations over there. Enjoy. Was that? All right. All right. We will stop over here. Thank you guys for your patience. We will meet again on Monday.